Hello, welcome back. And thank you to be here for this last part of the afternoon. It's been a kind of long day, but we are, I think, very happy for what we have heard. And now I have the pleasure to introduce a further alumnus, again, first cohort. And he actually represents here alumni and also a partner, because he now is working at ARPAE in Bologna, at the Environmental Protection Agency in Bologna. I tell you a little story about Luis. He was an excellent student. And then when he was close to finish Wacoma, he applied for a PhD and he won the first position in probably the most recognized PhD in Bologna. But then he had also an offer by ARPAE to work with them. He decided to go for the experience, the work experience in ARPAE. Everybody is, of course, very happy, but I think has been also a challenge to choose one of the two. And of course, he had great success he's having great success in what he's doing. So congratulations, Luis. He remained also in touch with us. So I'm also very happy for this. So Luis, please, I invite you to at the microphone. Look out.
Can you hear me? Yeah. Better? Yeah. Okay, so I'll try to keep on time. I have like 40 minutes, right? Something like that. Okay, so as Professor Fabri said, my name is Luis Germano Biolchi. I was from the first cohort of the third Wacoma, together with some ex-classmates who are here today. And nowadays I work at ARPAE, the regional agency for the environment prevention and energy of Emilia-Romagna, and we have been doing some developments in terms of oceanographic forecast. That's the work I've been doing lately. And I put here this image today because it really represents something to me. Sometimes it's very good to get out of our comfort zone, and I would like to give these words as well to the recent graduates. Sometimes it's important, of course, calculate the risks, think about what you're doing, but taking a step outside of your comfort zone might be a good thing. And this also works for us at ARPAE as we are entering the realm of probabilistic forecasts, and that's a step out of our comfort zone, and it can be very challenging, but very rewarding as well. So I will say a few words about my beginning. So I come from Brazil. I studied oceanography or oceanology in the same place as Elaine, actually, at Federal University of Rio Grande. And after that, I did a master's in marine geology at the Federal University of Rio Grande do Sul. They sound very similar, but they are different universities, actually. And while doing my master's in Brazil, I got in contact with Professor Eduardo Barbosa, who told me about the Wacoma program. So I applied, and I was lucky to be one of the chosen ones. And then I came to Italy to do Wacoma in 2018. We arrived in August 2018, and we graduated in August 2020. And it was a very, very good experience. And during my Wacoma period, I developed my thesis, which was entitled Ensemble Technique for a Coastal Early Warning System, an application to the Emilia-Romagna coast, which I had as an advisor Dr. Andrea Valentini, who gave a talk this morning. My co-advisor, one of them was Dr. Beatrice Giambastiani, who is also here, and Dr. Silvia Nguendoli from ARPAE. And it was a very nice thesis as we left the realm of the deterministic forecasts. We entered a little bit in the probabilistic forecasts in what we call a semi-probabilistic implementation. And we managed to get the work published in January this year on the good journal, I would say, Coastal Engineering. So that was very rewarding as well. So Professor Elena asked me to say a few words why I chose ARPAI actually instead of doing the PhD, right? So it was a very difficult decision. It was very challenging because as a personal goal, I would like to become a professor. I like giving presentations as well, even though sometimes I'm very nervous, like right now. But I chose the job because I could apply what I had learned before. I could check if I was actually suitable for the work experience, and that was a very good reason for me. Another thing is that PhDs will always be there. So I'm not sure if I will be accepted to PhDs in the future, but I can at least apply because I know they will be there. And a job opportunity not always knocks at your door like they did to me. So that was another reason. And another thing is that I already knew the people at the agency, the way they operated, and I liked pretty much my colleagues. I liked to work with them, and I would say those were the three main reasons for me on choosing this job opportunity. Another important thing before I start the presentation, that's an internal joke I have with the Wacoma recent graduate, so don't worry, I'll not be drawing anything today. If you want to know some more details later on, you can ask me, but yeah, no drawings. So what do we do at ARPAI, right? At ARPAI, pretty much one of the main objectives or one of the main things we do is to work with the forecast, right? And we follow what we call operational forecasting chain. So every day, the models, the operational models at the agency, they are run in a kind of a cascading, let's say, framework. So first of all is the meteorological models, which we have two that are the most important ones nowadays, the Cosmo Consortium applications for the Italian and the Mediterranean territorium. The 5M is a 5-kilometer horizontal resolution, and the 2I is a 2-kilometer resolution application to the Italian territory. So with the outputs of the meteorological forecasts, we pretty much go towards two branches of oceanographic related models. One of them relates to SWAN. SWAN is the simulating waves near shore developed by Delft, which is a wave model. And we have it implemented in three different domains, one covering the Mediterranean, one covering the Italian territory, and we have some regional, not regional, but like local applications in different Italian geographic or geopolitical regions, so like the Emilia-Romagna. And the other side of the branch, we have the oceanographic models, so the circulation models. We have currently two. One of them is soon to be discontinued, is called ADRIA-ROMS. And the other one, which is the official model now, is called ADRIAC. It relies on an implementation of the original oceanographic modeling system, ROMS, coupled in a two-way with the wave. So pretty much, the wave model talks to the ocean model, and they exchange variables within a certain time step. So it's very important if you want to forecast, for example, storm surges. And after running these two models, the wave and the currents, or the hydrodynamics model, we use the outputs in terms of sea level from the hydrodynamics model, and we use the outputs in terms of waves from the wave model, and we force the morphodynamic model X-beach, which is the base of our coastal early warning system. Ooh. Here, ooh, sorry, yeah. So I don't know if everybody's familiar with a morphodynamic model, but a morphodynamic model pretty much accounts for the interaction of hydrodynamics and morphology. How does it do that? First of all, in order to run a morphodynamic model, we need initial topobathymetric profiles. So here in the figures on the left, I'm showing an example of topographic profiles, actually topobathymetric profiles, in a monodimensional way. That's the way our models, they are actually implemented. In order to do so, in order to collect a topobathymetric profile, normally we do these surveys with RTK GPS for the topographic part, so for the subaerial part, and we do the subaqueous part with an eco-sounder, single beam, multi-beam, if available, and we construct the continuous profile. So that's the basis of our morphodynamic model. After that, in order to run the morphodynamic model, we need boundary conditions, which are given by waves and sea level. The sea level are given in absolute values, so if you have a sea level of 0.79, that's going to be your forcing for the model, while the waves then they can be given in a spectral form, either 2D or 1D, depending on the way you are working. But you can also give the wave parameters as absolute values as well, depending on how you are setting up your system. So every day, we run this system for 16 profiles distributed along the coast, and we have calculations done based on the outputs of the morphodynamic model. So for each time step, the morphodynamic model gives you the run-up. The run-up is the maximum vertical excursion of the water, and based on the run-up, you can calculate the distance between the water and a building, or the distance between the water and a dune. It depends if your profile has a dune or if it's an urbanized profile with a building. So we use these two storm impact indicators called safe corridor width for natural areas and the building waterline distance for urbanized areas. And we get a graph more or less like this, one on the bottom right of the figure, which shows you how far the water is from your reference point in the profile. So the closer the water gets to your building, I think the more worried you should be. And that's how one of the decision supporting systems we have to inform the Civil Protection Agency and ask for their feedback every morning, pretty much, on the debriefings. So as you can see, this is a very linear one-way road, right? So meteorological model forces the hydrodynamics model, forces the wave model, goes towards the morphodynamics model, and then you have one output. One simulation, one result, one chance of being right. How do we do with uncertainty? We cannot deal with uncertainty. That's our answer. Of course, based on previous experiences, you might know what happened or what might happen, and based on the extreme event that might be coming, you have a better idea, but based on your intuition sometimes. And it's very difficult. So what we've been doing recently is to go from deterministic approaches, given in this image by the black dashed line, to ensemble forecasts. So instead of having one chance of being right, we have several chances of guessing. And based on a given behavior, you might know, or you might have more information on the outcomes of a possible event. So probabilistic approaches, like ensemble applications, they allow us to address uncertainties. And there are several sources of uncertainties when you do modeling. One of them, for example, comes from the initial conditions, because we actually never know how the sea is when we start our modeling routine, because we don't have enough data. And we don't really know how the topobathymetric profile actually is at that moment, because we do seasonal measurements. So there are several uncertainties. One of the ways to avoid them is by doing an ensemble approach. We also have model-related uncertainties. They come from the parameterizations, because a model is wrong by nature. If it was not a model, it would be reality. A model simplifies the real world. So you have to parameterize your model the best way possible through calibration and validation procedures. That's also a long step to take. And the resolution, the length, and the number of members can also help you on addressing several uncertainties. So, as I said, if you do just one simulation, you have one forecast, it might be very, very difficult to reach the final predictability of that single event you're trying to forecast, right? Another important thing to mention is that the Italian Civil Protection Code allows or provides for the transmission of forecast in probabilistic terms. That's also very, very important, because besides having the technical capacity of doing probabilistic forecasts, we also have the legal background doing so. The Italian code allows us to do so, so it means we can, right? And for this reason, ensemble type forecasting models they can be used. So real quick, showing a little bit of the developments of our modeling systems. So the probabilistic coastal early warning system is a work in which I started during my thesis, then we got published, as I mentioned before. And we are actually expanding it during the STREAM project, as Andrea Valentini presented this morning. So one of the objectives of the STREAM project is to enhance our forecasting capabilities. This probabilistic application, instead of using the outputs of our hydrodynamics and the outputs of our wave models, we use the transnational multimodal ensemble system, which has been developed during the Ice Storms project a few years ago. And the TMAS uses 6 ocean and 5 wave forecasting systems. And they provide their outputs in terms of mean and standard deviation. So they combine, they put everything in ensemble, they give you the mean, they give you the standard deviation, and if you want, you can play with those and see what happens, and that's pretty much what we did, right? So here on the scheme, you can see the TMAS, so the significant wave height, period, and direction in the sea level provides the variables mean and standard deviation. So we decide to combine the variables mean and the standard deviation in different ways and force our X beach. So instead of having one forecast, we will have 4 forecasts or 3 forecasts. And that's actually a better way, the way we found to use those systems coupled and to have some uncertainty evaluation, let's say. So in the graph, you can see a 48-hour forecast here. You have the deterministic run in the green solid line, and you have also the shades representing the upper and right bound, the upper and lower bounds of the system being forecast with the TMAS. So the lower bound of the green shaded area implies that the water is actually closer to your reference building. So this has been run using the TMAS mean plus 2 standard deviations. Also, we ran using the TMAS mean and the TMAS mean minus 1 standard deviation, and we got an idea on how much the water, the range of this distance would vary during a forecast. So let's say during the first time step over there, you can see that the water might be between 45 and 85, 90 meters from the building. So it gives you already a measure of uncertainty of the system. So we decided to implement it in a different way now. We're improving this initial application, and now we're combining the 4 parameters that come from the TMAS using the mean plus 1 and mean plus 2 standard deviations and playing with those variables. So pretty much we have 3 values for 4 different variables, which gives us 81 members, I'm sorry. And in this graph, it seems a little bit confusing. It's like a macaroni type, let's say. And each of these lines is a different member of the forecasting system. So based on 81, we can start calculating exceedance threshold. So let's say that 70% of those members are below a given threshold. It gives you a stronger information to decide on, let's say, implementing defenses against a coastal flooding, because there is 70% chance of inundation happening. So it's a little improvement of the previous system I showed. Ooh, I went, okay. So besides the coastal early warning system in a probabilistic way, we also started an implementation of an oceanographic modeling system. So this one uses a finite element model called CHIFEM, and we are starting the implementation on a Mediterranean basin scale. And CHIFEM is a finite element model, so it allows you to resolve the very, very complex bathymetries. And we range from 5 kilometers of horizontal resolution to up to 200, 250 meters close to the coast. So you can actually forecast the total water level for specific locations, like the station of Porto Garibaldi that I'll show later. So we have done the initial implementation of this model using different atmospheric forcing. So instead of running with one atmospheric forcing, one atmospheric forecast, we did with 20 different ones. So we get distributions, we get differences or similarities, and we can interpret having more information, having more background of what's happening. So each one of these maps represents the same time step, and based on the differences or on the similarities, we can see more or less predictable events. And here, just a quick comparison to finalize. We measured one of the members we used to do a comparison with the measured sea level at Porto Garibaldi, and we actually found a very good agreement. And what was important for us is that, let's say, on the 5th of April, at the very beginning of the graphic, we have huge differences in the forecast that actually come from the different atmospheric forcing. And that's important for us to understand in terms of predictability what's going on and what's not going on. And you can also see this different distribution on the probability density function that I'm showing here on the bottom right. So it gives us a better idea, it gives us an idea on the variability of extreme events. So that's pretty much it. I'm already above my time, and thank you very much.
I must say that Luis is also very welcome and loved by the Wacoma students and also in the teacher community. So thank you, Luis, for being so nice and then being in touch with all of us. And of course, the new graduates can take example from him and also from Tegan, and imagine their future brilliant as young scientist as in fact is Luis. Do you have any question? Hi, please.
Oh, okay. Should I repeat everything?
Yes, repeat it.
Ah, okay, sorry. So, how far in the future does this forecast go? Let's say, I don't know, 1 day, 2 days, whatever. And also, do you have any idea, or have you done any exercise with you mentioned also the civil defense, on, like, what is the response time? Let's say, okay, you forecast an event to 1 hour from now. Can they still react, or how many hours do they need, or something?
So in terms of how far on future the forecasts go, we start them 24 hours before day 0. So let's say today's forecast we start yesterday. We run for 24 hours in what we call the spin-up period. So we warm the model up, and then we have from 0 to plus 72 hours of forecast. So we forecast 3 days. And in terms of the civil protection defenses, how long it takes for them to respond, I wouldn't say, because as I was attending the lecture this morning, I'm just the technical Apple. So the thing is that their training is actually in which we also talk to the civil protection, but every morning there is a debriefing in which they see if the conditions are going to be rough or not, if they should put the defenses on place or not. So I think the defenses, they can vary from a few hours to up to days, depending on the magnitude of the event. But I cannot be more precise than that. I'm sorry.
Fair enough. Thank you very much.
No problem.
Any more questions? So should we thank our Apple here? You are a very nice apple and shining. Good luck for your future. And then, well, I'm happy to introduce you another young person here, Italian in this time, a former student of the Italian course in Analisi e Gestione dell'Ambiente. He started working during his internship and master thesis at Kintex, and then in Agnes Power. They are, this is a top company in Ravenna right now, having many different also society around the world. But I mentioned as a top company because they are proposing the wind farm, the wind park in front of Ravenna. So they are having many seminars and exchanges with the ministry for, of course, this important project. So Pietro Solaroli is here to speak about his experience in the company and about the company. So the company is not an official partner of, associate partner of Wacoma, but they actually hosted many of our Wacoma students. And I would say that they also hired one of our students like Ruth Cuenca, and also they hosted Victor Almeida in these days, so in these weeks. So we are in these weeks, in these months. So I'm very happy for the interactions we have with this really brilliant company. So Pietro, thank you very much. I leave you the stage.
So, good evening, and thank you, Professor, for your introduction. Today, I would like to give you a quick overview of the Agnes project, in particular the Ravenna project, and the authorization procedure and the activities involved in the environmental impact assessment. So, Agnes, how can I? Okay. Yes. Agnes, which stands for the Adriatic Green Network of Energy Sources, is a startup company created in Ravenna by engineer Bernabini, which is here, with the specific aim to develop renewable energy projects among the Adriatic Sea. So the goal is to enact the transition of the Italian Adriatic Sea to the renewable energy sources, which is very much needed today. So Agnes company is developing 5 renewable energy projects for a total capacity of around 3,500 megawatts of power. The Ravenna project, which is the one I will be talking today about, is the most advanced project with the authorization process started. Then there are 2 floating wind projects that are the Marche projects and Pescara project, which are in pre-feasibility assessment phase, and another fixed foundation wind farm in Porto Tolle, which is also in pre-feasibility assessment. And there is the Venezia project, which is on its near shore, is a photovoltaic solar plant in developing in an artificial island in the Venice lagoon, and this is is quite advanced as well as the authorization process is ready to start, not yet started. So the Ravenna project is one of the first energy hub in the Mediterranean. Why I say it's an energy hub? Because it combines different renewable energy technologies, which are the solar, floating solar, the wind farms, and the hydrogen plants for hydrogen production plants. So here there is a satellite view of the offshore components of the project. As you can see, most of the infrastructure are built, not yet built, but are to build beyond the 12 nautical miles border. It's distributed in two wind farms, two parks. The Romagna 2, which is the northern one here, and the Romagna 1. Romagna 2 has 50 wind turbines, and Romagna 1 25, for a total wind power of 600 megawatts. And here in the Romagna 1 area, you can see also the floating solar plant, which is meant to be 100 megawatts. The other elements you can see are the offshore electrical substation and sea cables to connect all the infrastructure and to deliver the energy to the onshore section of the project. You can see here the marine cable landfall zone is connected with the terrestrial buried cable by a transition joint bay, and the energy coming from the wind farms is delivered here in the electrical substation onshore, which elevate the voltage from 220 kilovolts to 380 kilovolts, and the energy is then delivered to the Terna electrical station. Terna is the operator of the national grid, national electrical grid. In the same area of the electrical stations will be built the battery energy storage facility and the hydrogen production plant. So the Agnes Ravenna project aims to create advantageous synergies between the sources of energy, between the project itself and the economic tissue of Ravenna. An example of that can be the positive interaction between the possibility to use oxygen, which is a byproduct from the electrolysis, from the hydrogen production, for the business of aquaculture, for the fish farming business. In fact, it's really frequent, especially in summertime here in the shallow waters of Adriatics, low oxygen levels. So the oxygen can be useful, can be used by the fish farms to re-equilibrate the oxygen levels, of course, in a really small and confined area. And another aim is to introduce major breakthroughs in the energy sector, such as innovative floating offshore solar system, solar plant, and also the green hydrogen production itself, and the development of a new type of turbine, of wind turbine suitable for the Mediterranean Sea, for the Adriatic Sea in the specific, which has lower wind velocity, lower wind levels than, of course, the Northern Sea. Of course, Agnes is an excellent catalyst for investments, for employment and innovation. Here on the left, you have the systems of the project, and their interaction are schematically displayed in this chart. So you can see the offshore wind farm, the floating solar, the substation, the oxygen for agriculture, and so on. So here are some key numbers of our project. The combined capacity, combined power of all the systems, so the floating solar, wind, and batteries, is around 750 megawatts of power. So 600 megawatts from the wind, 100 megawatts from the PV plant, and 50 megawatts of storage capacity. Then some of the part of this energy will be used to produce hydrogen. We are planning to build hydrogen park, so electrolyzer for a target capacity of 50 megawatts, and this will produce around 16 tons of hydrogen a day, which is more than enough to start supply chain in the industrial area of the port of the Ravenna Harbor. In terms of electricity production, is 1.6 terawatt hour of electricity is expected to be produced yearly, which is enough to power 500,000 households. And the total overall investments is around 2 billions of euros. So, of course, a project like this has to undergo really complex authorization process. The core, one of the crucial procedures of this authorization process is the environmental impact assessments. In fact, the Ravenna project is included in Annex 2 of the EIA directive, which consequently, our project is under the National Environmental Impact Assessment, which is really schematically shown here below. As you can see, the very first step of the EIA is the presentation of this document, which is the environmental impact study to the committee. So the environmental impact study is the key document for the EIA procedure. As you probably, most of you know, the aim, the goal of the environmental impact study is to individuate and evaluate the impacts of the project, and in order to elaborate mitigation or compensation measures of those impacts. This can be achieved through the combination of the three main frameworks of the project, which is which are the regulatory framework, the project itself framework, and the environmental baseline. So today I would like to give you a quick insight of on the several activities involved that we are performing to realize the environmental baseline of the environmental impact study. So, for example, the starting point is the geomorphological characterization of the seabed. This is really important to know, to get information about the elements on the ground of our installations, of our structures. And you can see here below, this is the ship track of our ship scanning the wind farm area. Oh, sorry. I don't know how to. Okay, scanning the wind farm area with different remote sensing instruments such as single beam echo sounder, side scan sonar, sub-bottom profiler, and this will provide precious information about elements such as pipelines, underwater pipelines, wrecks, shipwrecks, or other kind of wreck, and more in general targets of interest that can be furtherly investigated by ROV service, remote operated vehicle. Then another important water and marine sediments qualities are other important environmental components that has to be characterized before to have the baseline, the environmental baseline. So we planned sampling stations for the sediments and for the waters, and field parameter analysis for both of them. And for example, the samples of the sediment samples will be assessed, will be analyzed also for not only for the chemical or the chemical, yes, components, but also for the analysis of the benthic community. The water quality will be assessed as well in terms of microplastics, so will be performed the mantatrol sampling for the marine litter quantification. Underwater noise is another important component because, of course, the installation and the functioning of the project is will be noisy, will emit noise impact, and so it's important to define what are what is the baseline, the sound baseline of our area, both for anthropic and biological sound sampling. So we performed the 2 campaigns and with 2 sound sampling stations with hydrophones to get those information. Then a typical issue of wind farms is the risk of bird fauna colliding in the wind turbine, in the blades. So it is one of the most hot topics of wind farms, the bird fauna. It's really important to assess the frequentation, the utilization of the wind farm area by the bird fauna. So we planned and performed visual count surveys campaign performed by marine fauna observer specialists that collected data about species, number of species, behavior of those species, flight direction, flight height, which is really important for the modeling of the colliding possibility. Then, yes, the fish fauna as well has been characterized with 2 scientific fishing campaigns in different spots of the wind farm area. Every sample, every caught species has been sorted and classified. Here you can see 2 pictures of the samples we gathered. Of course, those 2 stingrays were released. This is the same spot, Palo Bianco 1. And then, of course, another typical issue of the offshore installation is the marine mammals and sea turtles, which are very abundant in our project area. So, in order to get information, we planned 2 campaigns performed by marine mammals observers and also passive acoustic monitoring, and every observation during other campaign has been reported. And then on turning back to the onshore, also the coastline, the topography of the coastline, of the landfall has been assessed by photogrammetry, and a digital surface model has been made. As well, same as the underwater noise, as well the onshore noise has been classified. Of course, those studies I mentioned above is only part of the studies required for the environmental impact assessment. Here, here you can see a list of other studies. I can pick oceanography studies, atmosphere and air quality, navigation risk assessment. So the process, the path to the environmental authorization is still long. To conclude, I would like to give you a quick roadmap of our project. In the light blue arrows indicate the steps we already taken. we already achieved. And as you can see, we achieved quite a few important steps. For example, this one, the grid connection, national grid connection, has been secured into 2021, and the permitting process has started after the submission of the preliminary project. Now in 2022, we started the definitive project of field engineering design and, as I said, the environmental impact assessment study, when we aim to submit the EIS by the end of the year in order to get the environmental impact assessment started by the early 2023, and hopefully acquire all the permits by the 2024 and start to design the executive project. So the aim is to start to build in 2026, end of 2025. So thanks for your attention. This is it.
Thank you, Pietro. It's very nice. It's a pleasure for us to see our students getting into the real world and be involved in such important projects. Also, thanks the president and the owner of the company, of the Kintex company, to be here. Thank you very much. I know that you are involved in many interactions with the government, so thank you to find the time to be with us. And thank you again, Pietro, and I look forward to seeing the projects really going on. If you have any questions on this. Yeah, sure. How, wind farm? Yes. Yes.
Hello. I wanted to ask you two questions.
Yes.
I'm not sure if you answered the first one, so I will repeat.
Okay.
What's the distance? You said that it's within the territorial sea,
It's
like the
more,
12.
it's beyond the 12 nautical miles. It's about, it's the first turbine, it's about 13 nautical
Kilometer.
miles.
Okay.
13, 14.
Okay. So it's after the territorial sea.
Yes, yes,
Right.
it is.
Okay. And my next question was, what are the major challenges that you have faced with the affected stakeholders?
The major challenges is the difficulty to understand. Often it's not really clear the path you have to follow for the authorization. So it's really often unclear what to do, I mean, in terms of also of documents, what to produce to submit to the authorities, and what authorities you have to.
Yeah, I'm sorry, I'm asking more for the affected stakeholders, like fishing groups,
Okay, yes.
touristic groups.
Yes, one of the most difficult interactions is with the fishermen, of course, because all the wind farm area will be prohibited for fishing, and so it has to be found a point in common, point of understanding. So yes, it's one of the most difficult relationships.
Okay, thank you.
Thanks, Pietro. That's very interesting. As you know, around the world now, we've got many wind farms. I mean, the largest one in the North Sea that's now being built is 1,000 turbines. I've been involved quite a lot in designing monitoring programs for wind farms and indeed carrying them out. And one of the questions that you have to ask yourself is, what change are you hoping to detect from the monitoring that you're carrying out? For example, one company was told to monitor the benthos, and they were allowed to do 4 replicates at a station. But the degree of change that they were wanting to detect required 75 replicates at a station. So you then ask yourselves, are you doing the monitoring just to characterize the area, or are you monitoring it to pick up a certain amount of change? What we call the signal-to-noise ratio. So when you start monitoring, you have to determine what is the signal we're trying to detect against background noise. We can discuss this all later. But you also have to ask yourself, there's two phrases of the information you need. Is it nice to know, or is it need to know? Is it needed? Now, if you ask me as a biologist, I want to know everything. I want to know how the whole biological system works. But if you want to know what do you need to know in order to get this thing built, and I'm a great fan of wind farms, but what do you need to know? Then you have to ask yourself why you're doing certain monitoring. And some of the things that you're doing, such as 2 surveys for fish, wouldn't characterize the seasonal patterns. 2 surveys for mammals wouldn't characterize it. A very precise question to try and save you some money is, why are you doing a survey for litter when the development you're creating is not going to have anything to do with that, and the litter you're detecting is nothing to do with it? It comes from, let's call them messy people on land that's throwing things into the water. So I think you need to ask yourself, are you doing the monitoring just to please somebody, or are you doing it just because you need, or because you need the information?
Regarding the litter, I can answer to that. We must do it because it's one of the things that the ministry wanted from the developers, wind farm developers, to assess. I agree with you. It's not probably not our our impact, but it's precisely they ask precisely for the litter.
Yeah, this is a problem, Pietro, that we have.
Yes.
There was one wind farm I was involved in, and the scientists were told to monitor the phytoplankton and the zooplankton. Now, there is no way that the wind farm is going to affect the phytoplankton and zooplankton, but they were going to spend something like 300,000 euros monitoring it. And what you have to ask your ministry is, why the hell do they want litter monitoring? And why are they wasting your money, which eventually gets passed on to the public, because you're going to have to make the public pay for the energy. So, yeah, sometimes we have to challenge these things.
Yes.
Although it might be easier for some of us to challenge it than, you have to follow the regulations.
Unfortunately, but I totally agree.
Yeah. We'll talk later, that's good.
Yes, sure.
There's one more question, then we move on, but Pietro is certainly available.
I have a quick question. If it's too far from the coast, how are you going to bring the energy to the people?
The energy will be delivered with the export cable, which is at a higher tension. The higher is the tension, the more distance you can travel. Your energy can travel. So, as maybe you have seen, I don't know if I can go back, but in the center of each wind farm there is a platform, which is a electrical substation that elevates the tension of the energy coming from the generators from 66 kilovolts to 220 kilovolts. And that voltage allows the energy to travel such distances.
Well, this question probably is kind of silly, but it's because I don't know the legislation here in Italy. But do you have a specific set of guidelines that tell you, okay, you're gonna do environmental impact assessment for these particular projects, so you need to have like these elements, and maybe it's related to what Professor Mike Elliott was saying. Like, do you have a way to say like, okay, no, we are not gonna do this because this, or like you just need to follow it?
Yes, this is a really good question. Yes, usually there is. For offshore wind is still under development, and that thing, the marine litter classification is on the first, the early document of these guidelines.
Okay, okay.
Another question, a lot of interest. Very good. Thank you, Pietro. And then, yeah, the last talk of this morning is Antonio Persichetti and Tommaso Beschi from Archetipo. It is also a company which hosted some of our Wacoma students for the internship. So I'm really grateful, and thank you to be here.
Good evening. I am Tommaso Beschi, and I am part of the Archetipo company in Padua, where I deal with GIS analysis, processing of images from drones and satellites, and software development. I also speak on behalf of Dr. Antonio Persichetti, founder of Archetipo and head of the environment, agriculture, and research and development sectors. We thank you for the invitation to this symposium. In particular, we thank Prof. Sonia Silvestri, who strongly wanted us here, and with whom we collaborate in various research projects. Archetipo is a company that provides high-tech services for territorial survey. In Italy, we are a leader for the use of these technologies in many sectors, such as the monitoring of photovoltaic systems, monitoring of buildings, and in precision farming, for which we elaborate prescription maps and land use control maps. In the environmental sector, we treat about surveys for geological and hydrogeological instabilities, elaboration of digital elevation models, and monitoring of rubbish dump. We use multi-copter UAVs and fixed wind UAVs for more bigger areas. They are equipped with different optical sensors, such as RGB cameras, thermal cameras, multispectral cameras, hyperspectral cameras, and LiDAR. The first study case I want to show you is about a research born from the collaboration between the University of Padua and some other researchers from the University of Bologna as part of the Venice 2021 project. The target was to estimate the variations in the sediment supply on salt marshes caused by MOSE, a system for the lagoon protection from high waters. With on-field measures, remote sensing, and modeling tools, researchers could quantify the contribution of high water to the increase of the salt marshes and the modifications derived from MOSE. This study provides a method that can be applied to other lagoon and coastal systems characterized by the presence of mobile barriers. We focused on a 60 hectares area near San Felice, for which we aimed to obtain a 3D model of the area and to determine some characteristics of halophilic vegetation. We used a UAV equipped with LiDAR that allows to obtain in short time a digital elevation model with a large amount of data and a very high resolution. In LiDAR surveys, the point clouds data are automatically associated with high-resolution images so that it is possible to define details more accurately. Another UAV have been used with an hyperspectral sensor that takes images with 270 bands with a wavelength from 400 to 1000 nanometers. Hyperspectral cameras have an high potential for environmental monitoring. The sensor uses the different object reflection property in the electromagnetic spectrum determined by its chemical physical characteristics. From hyperspectral data, we can elaborate false color images of the observed surface. Okay. Here you can see the point clouds from LiDAR. With this data, we can also investigate the soil micromorphology. In these two false color images, we see two different representations of the area. The colors represent the intensity of the surface's reflectance for the different wavelengths. The acquired data were then reworked into vegetation indexes, combining the images acquired on certain bands with appropriate algebraic formulas. We can see plant biomass and calculate the CO2 capture capacity. Another project in which we are involved with the University of Ravenna, in collaboration with the team of Sonia Silvestri, is the Interreg Italy and Croatia Cascade project. The aim is to enhance the knowledge and the vulnerability evaluation of the internal coastal and marine ecosystems in Italy and Croatia to restore threatened species from extinction. We dealt with the definition of the innovative monitoring techniques for these ecosystems. We surveyed the Lago delle Nazioni, a brackish artificial basin extended for 100 hectares in the province of Ferrara. Near to the shore, this basin is near to the shoreline. We used an hyperspectral camera to scan the water surface in order to detect superficial microalgae. Meanwhile, researchers took some water samples. Thanks to the hyperspectral profiles of the 3 different microalgae species and their comparison with the water samples, we could observe their specific spectral response that allowed us to distinguish the algae groups one from each other. The study I show you now concerns survey activity for sluices in Cavallino Treporti in northern Venice Lagoon. In the Cavallino Treporti area, the sluices are in the final point of minor channel that allow the discharge of water in the lagoon. This manufact is always provided with regulation bulkheads in order to let the water flow in only one direction. We used drone and high-resolution RGB cameras to elaborate 3D models to evaluate their damage state and to plan their maintenance. This survey technique simplifies the traditional survey techniques that are very difficult to conduct in this kind of context. Using drone, we can obtain measurable 3D model, adopting the right photogrammetric procedures. We use drone also for the hydrogeological instability monitoring. In this case, we can see that there was a collapse of the riverbank, and with a thermal camera, you can see now when the vision is reached in the thermal, we can see the collapse of the riverbank. This is an example of the thermal images elaborated, and this is the image during the processing on a GIS software. This is another potential use of LiDAR that allow us to clean the point clouds from the vegetation and we can obtain the DTM, that are digital terrain models, cleaned by vegetation. We work also with multispectral data from satellite for precision farming. We use Sentinel-2 data downloaded from the ESA Open Hub service. From this satellite data, we calculate vegetation indexes for plant strength and leaf water amount in order to detect stress situations. Finally, the indexes are processed to create variability maps that can be used on variable rate technologies to allow the farmers to focus their resources only where the field needed to be fed. Using these systems, farmers can spare about 30% of water and chemical products. Archetipo, in the last years, developed a back-end software that can elaborate variability maps and vegetation indexes for a lot of parcels around the world. I ended my presentation. Thank you for your attention. And this is our email. If you want to contact us, take a note about it. Thank you.
Thank you. Thank you very much. Thank you to have accepted our invitation. And if there are questions, of course, what they do is very useful in your field. So keep memory of the email, and maybe you write them. Questions or not? Yeah, we can end our day here. And thank you very much for being here. And so thank you, everyone. It's been a nice day, very many informations, many thoughts. But we are now a bit tired, so we need some rest until tomorrow morning. And don't go to bed too late, because I just look at Renan. You know why. So anyway, thank you. Thank you all very much, and see you tomorrow morning, unless we meet around in the rest of the day. Ciao.